Yo, 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 what's up, class? Hope you're ready to learn some math this year. Start off with a video on real numbers, the first section of Algebra 2 Honors. Friendly reminder, and you'll get these on every video, you want to take notes, just because it's a good habit to get into, and also I might check them in class. What's beautiful about videos is that you don't have to slow down the class to ask questions or ask me to re-explain things. You can simply pause and re-watch the parts that are confusing. And any questions that you might have that cannot be answered in the video, please write them down so you remember to ask about them in class. Alright, so we're going to start off with some real numbers. Real numbers are just numbers that describe quantities in everyday life. Pretty much any number that's not a complex or imaginary number. And those two we'll talk about later, but they kind of go hand in hand. The real numbers could be broken down to two categories. You got rational numbers and irrational numbers. 2, pi, 2/5, 0.7, that decimal that goes on for a long time, and root 2 are all real numbers. Pi and root 2 are irrational numbers, and so is that decimal that goes on without any pattern, and the other three are rational numbers, and we'll learn about the difference in a second. One thing to point out, there is a one-to-one correspondence between real numbers and points on a number line. That means every real number has a place on a number line, and there's an infinite amount of points on that number line. So, rational versus irrational numbers. They are both subsets of the real numbers. Any number that is a real number will fall into exactly one of those categories. What makes a number rational is that it can be written as a ratio of two integers. Irrational numbers cannot, which is why pi and root 2 are irrational. Those are decimals that go on forever without repetition, which means, or any pattern, which means that they cannot be expressed as a fraction. So this first example right here, let me try this drawing thing here. Nice. 0.4 repeated, that is a rational number because it can be expressed as 4/9. What's cool about any number over 9 is just that number repeated, 1 through 9. And also 1.0909 repeated, that is 12/11. 12/11. That, although it is a decimal that goes on forever, it does have a pattern. Therefore, it can be expressed as a fraction. Therefore, those are two examples of rational numbers. 0, also a rational number. That could be expressed as a fraction. Just 0 over any number, that's not 0 really. And then these other two, root 5, the square root of any non-perfect square will be irrational. Because if you were to express it as a decimal, it would go on without terminating, without any pattern. Same thing with pi, which is the ratio of a circle's circumference divided by its diameter. If watch some of my geometry videos, you can learn a little bit more about pi. Oh, and right as I was talking about pi, I was at minute mark 3 minutes 14 seconds. That's pretty cool. Alright, so subsets of the rational numbers. We got natural numbers. Alright, first, the reason why they're called natural numbers, if you were to naturally just start counting, you'd probably start with 1, 2, 3, and so on. But the point is you start at 1. So natural numbers, oops, my bad, still learning this. Natural numbers start with 1. Whole numbers are the natural numbers plus 0. So pretty much all non-negative integers. That's another way to look at them. Then integers are all the whole numbers, but they could also be positive. Alright. Complex numbers, we'll worry about them when we learn about quadratics, but they help us to find numbers when we have to take the square root of a negative number, which would not be a real number. And again, I just want you to know that they're there, and they're not real numbers, but we'll learn about them deeply later on. Alright, so here's a Venn diagram of all the number sets. So within the complex numbers, which what I was just talking about, are the real numbers, which could be broken down into two categories, irrational and rational. And this space right here that I'm coloring in with red pen, it's kind of, there's no numbers there, so this is a little misleading, this Venn diagram. Numbers that are real are either irrational or rational. And then within the rational numbers, you have integers, which are kind of whole numbers that could be negative or positive. And then within the integers you got whole numbers, and then the natural numbers is just anything but 0. So 0 is just chilling in the whole circle. So it's an integer, it's a rational number, but it's not a natural number. 1, 2, 3, those are the rational numbers. Dot, 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 going on to infinity. Alright, let's talk a little bit about interval notation. So if you wanted to express all the numbers between two numbers, let's say A and B, and include them, then you would use these hard brackets. So if I wanted to express all the grade levels that go to Ridgewood High School, I would do 9 through 12 and then put hard brackets in between in order to include them. If I wanted to exclude the endpoints, then I would use parentheses. So if I wanted to say, all the ages or let's say you have to be a certain height to ride a ride, and you have to be over 40 inches, so 40 inches was too small, I would say, right, you have to be taller than 40 inches to infinity. Maybe not the best example, but there'll be more examples later. Pretty much the hard bracket means you're including that endpoint number, and the parenthesis means you're not including that number. And you can mix them together, like if you wanted to talk about all the numbers greater than A, but less than and including B, you would use the fourth one down, parenthesis and then hard bracket. And if it's an unbounded set, so the first four are all bounded because you have a set of numbers with two boundaries on either end. If you had an unbounded set, that is like x is greater than A, so you want to go from A to infinity, then you just simply go parentheses A, if you don't want to include A, to infinity, and infinity always gets a parenthesis. If you wanted to go, all numbers greater than or equal to A, then you'd use a hard bracket, a square bracket. I'm not really sure what they're called. I call it a hard bracket, as opposed to a parenthesis, which is, what that is. All right, and it could also be if you're talking about, all numbers less than B, then you want to go from negative infinity to B. When you use this interval notation, you always want the number that's less on the left and the number that's greater on the right. All right, and we'll do some examples. I'm sure you'll get the hang of that. So, express the following in interval notation. So, x is at least 48. So, that means x is greater than or equal to 48. So that's how it would look as an inequality. So in interval notation, you'd start at 48 and then go all the way to infinity. Let's say A is a number between 1 and 12 inclusive. So that means A is less than or equal to 12, but also greater than or equal to 1. So that would be as an inequality. As an interval notation, it would be from 1 to 12, and they'd be hard brackets because it is inclusive. You're including 1 and 12. But let's say P, number 3, is greater than -7, but less than or equal to 11. All right, so we don't want to include -7. We want anything bigger than -7. So like on a number line, we put an open circle on -7, and we want all these numbers all the way to 11. And we want to include 11, so that would be a closed circle. And we'll do more of that later. Now, as an interval notation, we'd give a parenthesis and put -7 on the left, because that's the smaller number, and then go all the way up to 11 and put a hard bracket, because that's the bigger number. That's why it's on the right, and it's a hard bracket because we want to include it. All right? It's just a few examples. Probably a good idea to put them down in your notes somewhere. All right, absolute value. So it is defined as the distance between the number and the origin on a number line. So what's the absolute value of -7? It's 7, because it simply describes how far away -7 is from the origin, or 0, on a number line. So the absolute value of negative 7 would be 7. So if you understand absolute values as if it's positive, keep it positive. If it's negative, make it positive. I mean, that's not the actual textbook definition, but that'll get you pretty far. It pretty much just makes negative numbers positive. But technically the definition is how far away that number is from 0 on the number line. So if you were asked to evaluate an expression with an absolute value in it, we're going to use this definition, which let me go back to this previous slide. We're going to use this definition. If what you're taking the absolute value of, in this case A, is greater than or equal to 0, then we're going to then the absolute value of A will equal A. We're not going to do anything to it. But if this number we're taking the absolute value of is less than 0, then we're going to put a negative in front of it to use double negatives to make it positive. Alright, so let's go on to this example. So we have the absolute value of 2x plus 6 over x plus 3. Now, alright, this example is probably pretty advanced for a first example, but bear with me. I'm just simply going to use the definition on the previous slide. So we have 2x plus 6, and that's in absolute values. Now, if 2x plus 6, that's what we're taking the absolute value of, is greater than or equal to 0, then our expression is pretty much going to stay the same. It's going to be 2x plus 6 over x plus 3. See, because 2x plus 6 is in the absolute value and it's positive, we defined it to be greater than or equal to 0, then the absolute value is not going to do anything to it. Just like if we had the absolute value of, why is my stylus not working? The absolute value of just positive 7, it would just equal 7. The absolute value is not going to change 7. It's going to stay 7. Alright, so that's their first case. You take what's inside the absolute value, say it's going to be positive or 0, and you rewrite the expression without the absolute value, and then try to simplify. Now in this rational expression, you can factor out a 2. Ignore this part up here. I didn't learn how to erase yet. Factor out a 2, and you get 2 times x plus 3 over x plus 3. And then these x plus 3's would cancel out, and you get 2. Alright? Now one thing we haven't learned yet that you got to keep in mind of is that you can't divide by 0. So we want to make sure that x cannot be negative 3, or else it'll make this expression undefined. So if we go back to this inequality right here, we can simplify that by subtracting 6 and then dividing by 2, and you get x is greater than or equal to negative 3. Alright, so that's the first part of our solution. If x is greater than or equal to negative 3, then the expression will just equal 2. And if you pause the video real quick and just plug in numbers into this expression that are greater than negative 3, you'll get 2 every time. Now, greater than negative 3, not equal to 3, negative 3. I want to get rid of this part here because we talked about earlier, if you plug in negative 3, then you'll be dividing by 0. Alright, so we'll come back to that part of the solution in a second. Then, the next step is take what's inside the absolute value and say, alright, what if that's negative? What if we're taking the absolute value of a negative number? Then, this expression, 2x plus 6, which is negative because we defined it to be negative, the absolute value will turn it to be positive. Oh, I must have hit the, I don't know what happened, sorry. The absolute value will turn it positive. It's already negative, so by putting a negative in front of it, it's going to make it a double negative and turn it positive. Now the x plus 3 is not an absolute value, so that stays. And then if you factor out a 2, you'll have negative 2 times x plus 3 over x plus 3. That cancels out, and now you have negative 2. And then this original inequality here, if you subtract 6 and divide by 2, you'll get x is less than negative 3. Alright, so your final answer to this evaluation question is going to be 2 if x is greater than negative 3, and negative 2 if x is less than negative 3. Alright? So I encourage you to maybe pause that part and watch it again, or maybe watch the next two examples. So let's do another two right here. Alright, evaluate the absolute value of 3x minus 1. So now this one won't simplify as nicely as the other one, but the approach is going to be the same. We start off and we take what's inside the absolute value and say, alright, let's say that's positive. And if it is positive, then the absolute value is not going to do anything. It's going to be like the absolute value of 10 is equal to 10, or the absolute value of 0 is equal to 0, the absolute value of 100 is equal to 100. If you're taking the absolute value of a positive number, it's not going to change it. Alright, so this inequality here will simplify to x is greater than or equal to 1/3. So if x is greater than or equal to 1/3, then this expression is just going to equal 3x minus 1. And I encourage you to take any number greater than 1/3, plug it into the original expression, and then plug it into this expression, and you'll get the same answer. We're just simplifying it. We're evaluating. Alright, but what if what we take the absolute value of 3x minus 1 is less than 0? Then that means that 3x minus 1 is negative. But we're taking the absolute value of it. So we want to negate it, to kind of use double negatives to turn a negative into a positive. Alright, and if you distribute the negative, you get negative 3x plus 1, which you can rewrite as 1 minus 3x, which it doesn't really matter. Either one of these is okay. I always like to lead with the positive number. Alright, so this part right here, the inequality, that will simplify to x is less than 1/3. So if that's the case, then this expression, the absolute value of 3x minus 1, will be equivalent to 1 minus 3x. Alright, and these two parts right here, I'm going to circle, make up our solution. If x is greater than or equal to 1/3, then the expression is equal to 3x minus 1. If x is less than or equal to 1/3, or less than 1/3, then the expression is equal to 1 minus 3x. Alright, let's do one more. X squared plus 10. Now, this one's special because it's a quadratic, and whenever you square a number, if it's not 0, it's going to become positive, and if it is 0, it's going to stay 0. So let's approach this the same way we approached the other two problems. Let's take what's inside the absolute value and say, alright, let's say that's positive. Then we know that our expression will just stay the same. It'll be x squared plus 10. But let's say x squared plus 10 is negative. And I'm going to go back to the first one and say greater than or equal to 0. Let's say x squared plus 10 is less than 0. Well, then our expression will become negative x squared plus 10. Alright, but here's the thing. In this second expression, x squared plus 10 will never be less than 0. Because if we subtract 10 on both sides, we get x squared is less than negative 10, which is impossible. Can't happen. Because when you square a negative, it's going to become positive. If you square a positive, it's going to stay positive. If you square 0, it's going to stay 0. So those numbers will never be less than negative 10. So we don't have to worry about that. So we could just say that x squared, this expression will equal x squared plus 10 for all real numbers. And that r looks like this, is the letter, it's kind of the symbol for all real numbers. And this symbol right here means belongs to. So when I write x belongs to the set of all real numbers, or when I write these Greek symbols here, that's what that means. Alright, moving along. Alright, some properties of absolute values which are worth having in your notes. The absolute value of a number will always be greater than or equal to 0. The absolute value of a number a is going to equal the absolute value of the opposite of that number a. And number 3, we can multiply two numbers together, then take the absolute value, or take the absolute value of each number and then multiply them, and we're always going to get the same answer. On the left, it'll become positive at the end. on the right, we're multiplying two positive numbers. And kind of the same idea with 4. And then if you ever see a question asking you to find the distance between two numbers or two variables, then we're just simply going to take the absolute value of the two after we subtract them. So if I want to know like how far away is, 2 and 7, well, they're 5 away, but I could do 7 minus 2, or I could do 2 minus 7 and then just take the absolute value of that. Alright, so the distance between two numbers is simply their difference, and then you take the absolute value. Alright, so let's do some examples with those. The distance between 3 and 7 is 4. So if I wanted to express that with absolute values, then I would say, alright, it could be either 7 minus 3 is equal to 4, or you could say the absolute value of 3 minus 7 is equal to 4. But the two numbers that you're asking to find the distance between, you're going to subtract them, put them in absolute values, and then set that equal to that distance. Alright, started off easy there. Let's try a harder one now. The distance between x and negative 4 is at least 13. Alright, the distance between x and negative 4. So that is just going to be x minus negative 4, the absolute value of that, which is equal to the absolute value of x plus 4. So this right here, the absolute value of x plus 4, represents the distance between x and negative 4. How far away is x from negative 4? Well, it's got to be at least 13, which means greater than or equal to 13. And this right here would be your final answer. Alright, you could have done it the other way. You could have said negative 4 minus x, the absolute value of that. And then that you could actually leave it like that, or you could factor out a negative 1, and then you get your 4 plus x there, and then we got the absolute value of that is going to be greater than or equal to 13, and then we can use one of the properties from before to simplify this down to look exactly like the first way we did it. You're taking the absolute value of the product of two numbers and then rewriting it as the absolute value of one times the absolute value of the other. That's just going to become 1 times anything is itself, and then we get the same answer that we got when we did it the first way. B is at most p units from 7. So here it's not as clear what two numbers we're finding the distance between, but it says B is at most p units from 7. So p is the distance that B and 7 are from each other. So it's talking about the distance. We could rewrite this as the distance between B and 7 is at most p units. So we can write that like this. B minus 7, the absolute value of that, is at most. So it's going to be less than or equal to p. So the distance between them is going to be at most p. So it's going to be p or less. So there we go. We can write it like that. And you can always make up some numbers to see if it makes sense. Like, I'll let you do that yourself. Alright? You could have also said 7 minus b, absolute value of that, is less than or equal to p. Alright, just some quick vocab. Algebraic expressions. It's a collection of variables and real numbers combined with operations. So terms, those are separated by addition. So in this example on the bottom, we have 3 terms. So terms are separated by addition or subtraction. But remember, you can always write subtraction as plus the opposite. And then the coefficients are the numbers in front of the variable. So that'd be like 5, negative 11, and 32. So just some important vocab to be aware of. And let's see, sorry, 2 more slides. What happened? Oh, that's the last slide. Sorry about that. Alright, here are some basic rules of algebra that I'm sure you are aware of or at least heard of before, but I would definitely write these down. They come up a little bit on tests and quizzes. So, commutative properties usually deal with, well, not usually, deal with 2 terms, or like two quantities. So commutative property of addition just means you can add two numbers in any order. Commutative property of multiplication means you can multiply two numbers in any order. So like 2 times 3 is equal to 3 times 2. Associative property is kind of the same deal, except you're dealing with three quantities. So like if you were to add A, B, and C, you can add A and B first and then add C, or you can add B and C first and then add A, and you'd get the same number. Same thing with multiplication. Alright, so associative property of addition, multiplication, commutative property of addition, multiplication, both have to deal with, order doesn't matter in addition and multiplication, but commutative has to do with two quantities, associative has to do with three. Distributive property, well, I'm sure you're aware of that. That just means you have a number outside a parenthesis and a sum inside the parenthesis. Then you just multiply the two numbers inside the parenthesis by the number outside the parenthesis. Identity, when you see identity, think, all right, when you do this property, it's going to keep its identity. So what can you do to a number with addition so that it stays the same, it keeps its identity? Well, it's adding 0. So adding 0 is the additive identity. And then multiplying by 1 gives you the same number. So the multiplicative identity is just multiplying by 1. Inverse properties mean you do that operation and you get the identity. So like what could you do, what can you add to A to get the identity, which is 0? Well, it would be adding negative A. So inverse and identity kind of have a lot in common. You do the inverse to get the identity. So you add the opposite to get the identity, the additive identity, which is 0. With multiplication, the multiplicative identity is multiplying by 1. You can get 1 by multiplying by the reciprocal. So the multiplicative inverse would be taking a number A and multiplying it by 1 over A. It's just some annoying things you got to memorize early in the year. There won't be a lot of things you have to memorize, but these are some of them. And then last but not least, prime numbers. So an integer with exactly two factors, 1 and itself. And the fundamental theorem of arithmetic says that every positive integer can be written as a product of prime numbers. So like, I don't know, let's go with 40. So you got 2 times 10, and then 2 times 5. So 40 can be written as 2 times 2 times 5. Alright, now I'm missing something. I messed up. That's 2 times 20. Wow, that was silly. So it'd be 2 times 10, and that breaks down as 2 times 5. So I was missing it too. Boom, there you go. So that's the fundamental theorem of arithmetic, and we'll work a lot more with those later when we do radicals and rational exponents. Alright, I think that's the last slide. Yeah, it is. So thanks for watching. This first section is a lot of review from past math classes, geometry, and not really geometry, but mostly algebra 1, and all the cool stuff you learned in middle school. But sorry this video took so long. I'll try to shorten the other ones, but I think you'll like this flipped classroom a lot. Get to watch the videos, watch them as many times as you want, and then we'll have a lot more time to practice and get better at math in class, as opposed to you just sitting there listening to me talk the whole period. So I hope this experiment works out. Hope you find these videos useful, and see you in class.